Greetings and welcome to the complete lecture for Chapter 20 of Chemistry 222. In this chapter, we're going to look at nuclear chemistry, the chemistry of the nucleus. And all the other chapters we've seen up to this point have basically been the chemistry of the electrons around the nucleus, and they're obviously very important. However, in this chapter, we're going to see the kind of power and potential that the nucleus has to offer, and it's quite amazing. The energy levels in this chapter are quite large compared to the previous chapters. It's a pretty cool chapter. So let's see what this chapter has to offer. Sit back, relax, and let's get into the lecture. In previous chapters, we've talked about the composition of the atom, and it's worth reviewing here really fast. So an atom has a nucleus in the center of the atom. In the nucleus are the positive protons and the neutral neutrons, and around it circle, if you will, the electrons in the electron cloud. Electrons behave more like a wave that kind of envelops the nucleus and extends right on around, while the nucleus is very, very small, all right? If that was actually the size of an atom, the nucleus would be probably something so small we couldn't see it here in this picture. So it's pretty small. There's a lot of energy in the nucleus. So when it comes to the reactions within the nucleus, it's going to be much higher energy. And so the reactions in this section will look quite different from the previous chapters that we've seen. One of the results of nuclear reactions is radiation, and radiation is just a really high energy form that emits sometimes when reactions happen. Radioactive rays can penetrate and ionize matter, so it'll go through the matter and it will turn them into positive or negative ions, which isn't good, of course, for the structures. Radioactivity was originally discovered by Becquerel, and then later Marie Curie really took that ball and ran with it and did a lot more work on radioactivity. Radioactivity is pretty important. Even around us right now, we are experiencing some radiation. If you live on the Earth, and I'm assuming you do, then some radiation comes from the Earth up to us. Some radiation comes from outside the Earth to us through the sky. So it's a really powerful tool, and we're used to some radiation. So we'll talk in this section about what radiation is, what it can do, also talk about the types of reactions that create the radiation. On the periodic table, there are at least three really important portions that we've talked about before, but let's go through them again. One of the things that's really important is the atomic number, given the symbol Z, and the whole number listed to each element on the periodic table is the atomic number, and the atomic number is just the number of protons. So for aluminum right there, aluminum atoms always have 13 protons. So the atomic number is 13, aluminum has 13 protons. Those two things go together. However, you can have more than one version of the same element, and this got us into isotopes. So to figure out isotopes, we need to talk also about the mass number. And the mass number, which gets the symbol A, is equal to the protons plus neutrons for the nucleus. So as an example of this, boron is number 5 on the periodic table. That means it can have 5 protons, no problem. But boron can have 5 neutrons. We'll talk about why it sometimes doesn't have that too. So if you want to figure out the mass number for a boron atom with 5 neutrons, protons plus neutrons, 5 plus 5, 10 would be the mass number. And that symbolism in the lower right there with shows AZ, you can see that the upper left-hand corner is the mass number, the lower left-hand corner is the atomic number, and then the symbol goes kind of right there in the middle. So that would be the symbolism for boron 10. And sometimes the atomic number isn't showing because the hip chemist knows that boron with symbol B always has 5 protons, an atomic number 5. So sometimes the 5 is omitted to just have the superscript. Just kind of realize these are all the perturbations you can have. Now, because there are different isotopes, there are different versions of boron, for example. So boron 10 is around a lot, but there is actually a boron 11. So a boron 11 is a different kind of boron. It's an isotope of boron. The reason that boron 11 would be different is that the mass number A for boron 11 is 11. Now, boron always has 5 protons, so 11 minus 5, mass number minus atomic number, tells you the number of neutrons. So boron 11 has 6 neutrons. So while we just talked about boron 10, there is also a boron 11 with an extra neutron. The third piece of information for each element in the periodic table is the atomic weight, or the molar mass of the particular element you're looking at. So for aluminum right there, that's 26.9815. If you look at boron on the periodic table, it's roughly 10.8. And the atomic weight / molar mass number comes from the fact that it takes all of the isotopes and thinks about the abundance. So boron 10 is roughly 20% of the abundance of all boron atoms. So what that means, if you had 10 boron atoms, 2 of them, 20%, would be boron 10. But 80% or so are boron 11. So for the 10 boron atoms we have, 2 of them would be boron 10, and 8 of them would be boron 11. So all of those numbers together gives you the atomic weight / molar mass number of boron, which is about 10.8. So for aluminum there, it's about 27. All right, aluminum 27 is the most abundant isotope. There is, for example, some aluminum 26 and stuff like that. But notice how the atomic weight is very close to 27. That a lot of times is a hint as to what the most abundant isotope is. Great segue to this question. Copper can be found in 2 primary isotopes, copper 63 and copper 65. Which isotope is more abundant? It might be tempting to think more information is necessary, but what you can do is just look at the periodic table for copper. Now, copper is number 29. That's the atomic number. Copper has 29 protons. And here we're talking about 2 isotopes of copper, copper 63 and copper 65. If you look at the value for copper on your periodic table, it's about 63.5. And 63.5 is closer to 63 than it is than 65. You can think about like a number line between 63 and 65, the 2 mass numbers. Then the average mass, which is listed on the periodic table, 63.5, would be closer to 63 than it is to 65. So for all of those reasons, copper 63 is more abundant. Copper 63 is roughly 70% abundant, and copper 65 is about 30% abundant. And those are not things you need to know, but that's why the average mass, which is the atomic mass or molar mass, is closer to copper 63 than it is copper 65. The strong nuclear force is the name of the force that holds the protons and the neutrons together. And if you think about why this is important, we've talked about how positive and negative charges attract, but like charges repel. So negatives repel, but also positives and positives repel. And so in order to keep those positive protons happy in the very, very small nucleus, the strong nuclear force kicks in. The strong nuclear force is one of the 4 fundamental forces in nature. This is an overview of the 4 forces of nature. Now, gravity, the gravitation force, is the thing that holds the planets around the sun. It keeps our solar system circling the galaxy, and the galaxies is circling each other in the universe, all that kind of stuff. It's a powerful force, but it is relatively long range. Like, it works great about holding the moon to the Earth's orbit, that kind of jazz, but it doesn't do a very good job, say, holding you and me together if we were next to each other. So it's considered to be a weak force. Now, it's not that it's not like a wussy force, because wow, yeah, holding the planets around the sun is no small feat. However, it is a relatively long-range force, and when you compare gravity to the other forces we're going to talk about, it's one of the weaker ones, which is strange. Another force of nature is called the weak nuclear force, and it is a force that's responsible for giving beta decay. So every time we're going to talk about beta decay, it's basically due to the weak nuclear force. We're not going to talk too much about the weak nuclear force, but it is a relatively short-range force. It's not as helpful to us as the next 2 forces are, so honestly, I'm going to kind of gloss over it, but in physics, you'll talk about it a lot more. But the third force is one we've talked about extensively since Chem 221, and that's the electromagnetic force, or the EM force. And the EM force is considered relatively long range. It's the force that keeps electrons around the nucleus. And sometimes I've called this the glue that holds the atoms together. I don't know if you want to use that or not, but that is something that truly helps. All those positive, negative attractions, that's all the EM force, which is pretty cool. Now, the EM force, they have feel is 10 to the 36 times more powerful than gravity. So when I said gravity was weak, no disrespect to gravity, because it is important, it keeps us on the earth and stuff like that. However, it is much weaker than the electromagnetic force. Electromagnetic force is nothing to mess around with. Again, all the times I've mentioned Coulomb's law or Coulomb's forces and electromagnetic, EM, all this kind of jazz, that's all positive, negative. That's the electromagnetic force. But the fourth force is definitely going to be something to talk about. It's called the strong nuclear force. And the strong nuclear force is about 1,000,000, 10 to the 6, times more powerful than electromagnetic. Now, electromagnetic, as I said, was 10 to the 36 times more powerful than gravity, and EM is even, or strong nuclear force is even stronger than the electromagnetic force. So strong nuclear force is what keeps those protons next to each other in the nucleus, because positives and positives don't want to be there, but the strong nuclear overpowers them. However, the strong nuclear force has a very short range, and they feel it's about 10 to the minus 15 meters. It's a femtometer. That's the Greek prefix for 10 to the minus 15th. You don't need to worry about that. The important thing for us is that it's very, very short range. And we're going to see in this chapter that sometimes the strong nuclear force starts breaking down. Those positive repulsions in the nucleus start interacting, and it's going to be enough to break a lot of the atoms apart. However, as long as the strong nuclear force is active, it is a strong force. It keeps those protons and neutrons together. You can think about it as the glue that keeps the nucleus together. So while electromagnetic keeps the electrons around the positive nucleus, and that's a type of glue, there is a second type of glue here that keeps the nucleus together. So we'll talk about the interactions of electromagnetic and strong nuclear forces in the upcoming sections. Some nuclei are very, very stable, but there are a lot of nuclei that are unstable. And the reason they're unstable is because the electromagnetic force, which is relatively long range compared to our other force, the strong force, the electromagnetic force begins overpowering the strong force. So the strong force keeps those positive protons in check in the nucleus, but when it starts breaking down, the positive electromagnetic force, those protons interacting with protons and repelling each other, start to build up. They build up like friction, if you will, and it's going to be enough to break the nucleus apart. Now, you do get some stabilization through what's called magnetic dilution, because neutrons are neutral. And if you can have a neutral neutron between two protons, that does tend to separate them a little bit, and it does offer a little bit of stabilization. So we're going to see that the number of neutrons in the average isotope of an atom tends to increase as the atomic number goes up. Up to calcium, the most stable nuclei usually occur when the proton number is equal to the neutron number. And there are exceptions, but generally that's the case. So for example, carbon-12 has 6 protons, atomic number 6, and 6 neutrons. So the protons and neutrons are the same. And there are some exceptions to this, but overall that's pretty good. Now past calcium but up to lead, the most stable nuclei definitely have more neutrons than protons, all right? The number of protons becomes less than the number of neutrons. And you're just going to see that the neutrons are starting to help with this magnetic dilution. All right, it tries to keep the nucleus stable. But after a while, when you get past lead, essentially all isotopes are unstable, all right? They just will all break down. Now, sometimes people consider it's beyond bismuth, but recent studies have suggested that bismuth is unstable too. So that's why, generally speaking, it's beyond lead. All isotopes are unstable and radioactive. Now, sometimes the isotopes won't decay for like millions and millions of years. You can talk about their half-life. However, the important thing here is that they will decay. They are unstable. And the timeline reference point definitely has to be considered. Like, is it our lifetime or the lifetime of the universe? This kind of stuff. But past lead, it is considered that all isotopes will decay. Scientists have studied this behavior about stable nuclei and the unstable nuclei. And on the x-axis there, you have the number of protons, or the atomic number Z. On the y-axis, you have the number of neutrons, N. All right? So protons plus neutrons would be mass number. And if you look at this graph carefully, there's black dots in the middle and red dots on the outside. All of the black dots are considered to be stable nuclei. And so those nuclei aren't going to decompose. They're very stable. There's been no evidence that they break down, anything like that. However, on both sides of the stable nuclei, there's several red dots, which represent unstable and radioactive elements, and those will break down into different kind of processes. So if you use your imagination a lot, this particular graph right here is called the peninsula of stability graph. Now, a peninsula is a part of land that juts out into a lake, and so all around the peninsula you have water. All right, so in this version, the peninsula of the stability are the black dots. It's this little tiny part of land, if you will, that juts out from the mainland, and all around it is the ocean. Though it's not really an ocean, but it is called the Sea of Instability. So all of those red unstable isotopes surround the stable ones. So again, it's called the Peninsula of Stability in the Sea of Instability. And it's kind of a poetic kind of imagery that maybe pops in your mind, and that's what it's supposed to do. But you can see that as of looking at this graph, there are limits to how many stable isotope atoms there are. However, some great research has been done by some powerhouses of this field, and the two names that are most important, in my opinion, are Glenn Seaborg and Ken Moody, and they've studied these really super heavy elements and what they have, and they were the ones that helped recognize the peninsula of stability in the Sea of Instability. However, they have made predictions, and this is based on math, and it's definitely beyond our capacity here in Chem 222, but they have made predictions that there will be one day some islands of stability found, and the islands of stability will have true stable nuclei, very, very large atomic numbers, or a huge number of protons, but there's some evidence that suggests that this could happen. So eventually one day you might be able to use an element with, say, 250 protons or something like that. Right now the periodic table goes up to 118 protons, so imagine having something with 250 protons that you could use like aluminum or carbon. It's pretty cool. So maybe one day, we'll see, but it is fun to think about. To figure out the energy required to hold the nucleus together, we can do what's called a nuclear binding energy calculation. And the energy we're going to calculate in this process will be the energy required to overcome those positive repulsion of protons in the nucleus. And it's a pretty big number. The power is achieved by utilizing the strong and sometimes the weak forces, which we're not talking about as much. So it takes a lot of energy, but it is possible to overcome. Strong and weak forces are stronger than both the EM force and gravity, so that's why they become so important. So nuclear binding energy, which gets the symbol E sub B, is used to estimate the force contribution, mostly from the strong force, a little bit from the weak force, just to see like how much energy is actually required to keep the atom together. The binding energy, E sub B, it's the negative of the energy change, the negative of the delta E, if the nucleus is formed directly from the individual protons and neutrons. And I'm sure that's about as clear as mud, so let me give you an example to show you how you can figure out the binding energy yourself for any isotope on the periodic table. Let's calculate the binding energy E sub B for deuterium. Deuterium is an isotope of hydrogen. It's hydrogen 2. So hydrogen 2 has a mass number of 2. Hydrogen has 1 proton. So mass number 2 minus 1 for the atomic number means it has 1 neutron. In this process for binding energy, we're going to build this isotope directly from protons and neutrons. So to make hydrogen 2, we're going to need one proton and one neutron to make that happen. That's going to create the hydrogen 2. And notice the nomenclature there. Protons are often 11p like that, and neutrons are often 10n. And we'll come back to this later, but just realize that's the reaction we're going to look at. If you look carefully at the mass of a proton, which is that 1.0078 number, and the mass of the neutron, 1.00865, you'll find that those numbers added together are actually greater than the mass of, in this case, deuterium. So, and this works for all atoms, by the way. The protons plus neutron masses will be greater than the atom that you're actually looking at. So in this case for deuterium, all right, when you add the proton and the neutron up, you get 2.016 or so. And for the deuterium itself, it comes out to be 2.014 or so. So those numbers are not the same. There's actually a mass lost upon going from the proton and neutron to deuterium. Like you would find a delta M, final minus initial. That would be the deuterium minus the proton and neutron. It's the final state minus the initial state. And goodness gracious, we are losing mass. We have lost minus 0.00239 grams per mole. Mass is not conserved. And about this time, you're probably like, boy, Russell, I need my money back because we spent all that time balancing equations, and now you're saying that things aren't even balanced and stuff. And you're like, rah, rah, rah. And I understand because I feel that way too. Well, actually, that mass loss is really important. Einstein has an equation, which is E equals mc squared. And this is a famous equation of his. If you haven't seen it, it's no big deal. But what it is, it's a way to relate the mass of an object to the energy of an object. And how it's usually used is it's a delta E equals delta mc squared. C is the speed of light, 2.998 times 10 to the 8th meters per second. And the delta m part has to be in kilograms to make the units work out. So anyway, we're going to use that little bit of mass loss to figure out the energy used in the process, the energy that was obtained. So what we did right here, in the last slide, it was like minus 0.00239 grams per mole. We're going to turn grams per mole into kilograms per mole, and then we'll multiply that by the speed of light squared. So remember, use 2.998 times 10 to the 8th meters per second for speed of light. We'll multiply by c squared. And when you do that, you get a delta E of minus 2.15 times 10 to the 11th joules per mole. Now, before we go any further, I want to talk about that number because it's pretty spectacular. First of all, it's negative, so it's exothermic, all right? As you make deuterium, you get energy out. That's what the negative sign means. But another thing I want you to think about is the magnitude of this number, because this number is 10 to the 11th joules per mole is way above all the other energies we've looked at so far. For example, if you took a strong acid and a strong base and you reacted them together, it might be, say, 10 to the 6th joules per mole, all right? And you could figure out delta H products minus delta H reactants to figure these kind of things out, by the way. But anyway, those energies are much, much, much less than 10 to the 11th joules per mole. When you make things like deuterium, you are getting an incredible amount of energy out. Not just a little bit, but a lot of energy out. And we'll come back to that here in a little bit. The binding energy is defined as the opposite of the energy change. So basically, you want to turn that negative into a positive, and you end up in kilojoules with a value which is 2.15 times 10 to the 8th kilojoules per mole. And that's just a crazy, crazy amount of energy. So while a lot of the other things we were looking at were, say, 10 to the 3rd kilojoules per mole, this is 10 to the 8th kilojoules per mole. So it's just an incredible amount of energy. Positive version like that, they feel that's the energy saved through stabilization of the strong and nuclear force. So it's a pretty massive effect. It's not just a minor effect, it's pretty big. I like to think of these numbers as the justification for why the elements form, because making energy is kind of like making money in our world. And that's a weird way to think about it, but it's true. So as you make money in our world, woohoo, everybody celebrates and drinks champagne or whatever. Well, in the science world, if you can make energy, those are the reactions that usually happen. And this isn't making just a little bit of energy, this is making a lot of energy. So this is the reason why the elements form. So much energy is created that you end up then making all the elements you can, basically. That's why we have hydrogen and helium and lithium and carbon, et cetera, et cetera. And we don't have just protons and neutrons or pure energy for that matter around. A lot of times they'll figure out the binding energy per nucleon, and a nucleon is literally a subatomic particle in the nucleus. So basically count up the number of protons and neutrons, and that's going to be the number of nucleons. So in our example, we have 1 proton and 1 neutron, or 2 nucleons. So if you take that previous EB and divide it by 2, you get 1.08 times 10 to the 8th kilojoules per mole of nucleons. So for every nucleon you put in, you get that 1.08 times 10 to the 8th kilojoules per mole out. This is literally the strong force contribution to the nucleus. All right, it literally tells you how much energy has been saved, and it's considerable. All right, 10 to the 8th kilojoules per mole per nucleon is a huge savings. This is what the strong force does. It's an amazing force. So in the last slide, we calculated the binding energy per nucleon for deuterium, which is hydrogen 2. And this is a graph that shows the binding energy per nucleus for all different kind of versions. So down here at the bottom, this is where deuterium is. It was 1.08 times 10 to the 8th or whatever. So that's where that value is. And then you'll notice here, there's kind of like a curve, and it goes up to a high point of iron 56. We'll talk about this in a little bit. And then it starts to go down again. You can see all the way over there to uranium 238. And this is a really cool graph for scientists. First of all, we're going to talk later about fusion, which is right there, and fission, which is up in the upper right-hand corner. Lighter elements, smaller atomic numbers, elements use fusion to become more like iron, and heavier than iron elements will use fission to become more like iron. And we'll come back to that here in a little bit. But we're going to talk about what this means. But again, what I want you to see more than anything is that iron 56 is kind of the top of the hill, all right? And you can't go any farther than iron 56. So for example, deuterium could use fusion and more and more times to eventually become iron 56, but then it would have to stop. On the other hand, uranium 238, way over there on the right, it could undergo fission lots and lots of times until it got to iron 56, and then it would stop. So iron 56 is going to be a key to understanding the implications of this binding energy graph. So because iron 56 is the top of the hill, it really is the end point of everything in thermodynamics, all right? You cannot make anything past iron 56, more or less, once you get there. So for example, the sun, all right, the most massive energy source in our solar system, the sun, when it starts to make iron 56, it begins to stop. It no longer can generate the fusion in order to make more energy possible. So iron 56 is kind of the end point. And so if you have any kind of solar cycles or any kind of elements, iron 56 is kind of the final spot. So if you have an element that's less than 26 protons, less than iron, it'll use fusion, which we'll talk about later, to become more like the iron 56. On the other hand, the greater elements like uranium, krypton, molybdenum, etc., they will use fission to become more like iron 56. And if you think about this long enough, you can envision probably one day a universe of nothing more than iron 56. And at that point, all energy would stop because there's no more reason to have anything but iron 56 around, kind of a dark, dreary thing. However, I'd like to remind you that kinetics is a huge factor in this. Having any of these reactions possible takes incredible amounts of energy of activation. And so the time required to have the elements fuse or fission, become visible, is really, really large, all right? And multiple generations of children's are still going to be here, right? Assuming, the thermodynamics is not the end all here of things, but it is kind of an interesting topic to think about. Iron 56 is truly the high point of when you make things in fission and fusion. So this is a question you might see. It says, which of the following nuclei has the highest binding energy per nucleon? And it lists the lithium, a nickel, a helium, and a thorium. This would normally be kind of a difficult question to answer because how do you know? You probably don't have a table of binding energies nearby and stuff, and it's hard to look out. However, if you have to guess, which is basically what I'm forcing you to do in this problem, you want to pick the element which is closest to iron on the periodic table. And if you look at the periodic table, nickel is just a couple of elements away from iron, all right? You add a couple of protons and you'll turn your iron into nickel, or take a couple of protons away from nickel and you'll have iron. So the nickel compound here probably has the highest binding energy per nucleon. Now, I had the advantage of Google. I could look the different values up, and there are the actual binding energies per nucleon in what's called a mega electron volt. And a mega electron volt is equal to that 10 to the 13th joules. It's a massive amount of energy. So just look at the magnitudes of those different numbers right there. Nickel 59, 8.69 mega electron volts, much higher than the lithium at 4.88, the helium at 5.49, or the thorium 232 at 7.63. So again, the elements closest to iron should have the highest binding energy per nucleon. So in order to talk more about nuclear reactions, we need to talk about some special and unusual radioactive particles and energy types that we'll see in these reactions. And so this is where this gets kind of like a fun chapter. We're going to learn about nuclear equations and how to balance them, stuff like that. The alpha, beta, and gamma radiation types are something we mentioned briefly back in Chem 221, I believe it was. And they all correspond to a particle or an energy. So an alpha particle is nothing more than a helium nucleus. Now most helium is helium-4. So you can see the symbols right there. We have a 2 on the bottom by the He and a 4 on top. 2 is the atomic number of helium, and since most helium is helium-4, that's why there's a 4 right there. There is some helium-3 and other things, but most of it's helium-4, so it's a pretty good guess. Now sometimes instead of He, people will use an alpha symbol there. Alpha represents alpha radiation, which is what this is. If you've ever been to a birthday party, and they sometimes have balloons, all right, and if balloons are made with helium a lot of times, so if you kind of suck the helium in, you talk like a chipmunk for a while, ha ha ha, that's really great, you're really dumb and wasting brain cells or whatever. However, you wouldn't want to do this with alpha radiation. Alpha radiation is helium, but it's supercharged helium, and it would like bounce around in your body and it would do horrible, horrible things. So this isn't the normal version of helium by any means, and that's why sometimes it's given the little alpha symbol. But you can write He as well, and that's no problem. Now, earlier we did see a beta particle. Beta particles are supercharged electrons. So while electrons can turn chlorine into chloride and stuff like that, this as well is like a supercharged beta particle, and you wouldn't want to mess around with this by any means. Now, electrons a lot of times get the symbol E, and you're welcome to use that. You can also use beta, that symbol right there for it. But look at the numbering. It has a 0 for a mass number because it has no protons and neutrons. And for its atomic number, it has -1. And that's a little weird, but for right now, just take it as a leap of faith. There's a reason for it. Kind of crazy. So electrons, 0, -1, E, or 0, -1 beta. Gamma radiation is pure energy, so there's no mass at all. So there's no atomic numbers, no mass numbers, anything like that. It's literally pure energy. Gamma radiation is one of the electromagnetic radiation types we talked about. It's more powerful than X-rays, pretty powerful stuff. Once in a while, we'll see protons and neutrons as well. We saw, I believe, a problem earlier with a proton. Protons have 1 proton, so the atomic number lower lower left is 1. Protons plus neutrons is equal to 1 as well, so that's why you see the 1-1 symbolism. 1-1p or 1-1h for hydrogen, because that's basically what it is, no problem. And by the way, I should point out here that these particles, again, are supercharged version of their normal counterparts. So all of them will have the electrons stripped away. So the hydrogens in the protons will be positive, the heliums and alpha particles will be positive, but it's not a major energy component, so chemists will usually ignore it. So we usually just leave the upper right-hand corner empty where the charge would go. It's just assumed that the electrons have been stripped off a long time ago, but that's neither here nor there. Now, neutrons have no protons, so the lower left-hand number is 0. Protons plus neutrons would be 0 plus 1 or 1, so 10N is the symbol for the neutron. And finally, the best for last, the wildest of all of these particles is called the positron. And the positron is an anti-electron. Now, if you've ever watched Star Trek and shows like that, they'll talk about antimatter, all right? And antimatter, when it touches regular matter, it explodes, and it's a big thing in a lot of science fiction shows. And I love that kind of stuff, I won't lie. However, antimatter is real. It's a real concept. It's a very difficult form of matter to deal with because if it touches anything that's normal, it explodes. Lots of energy is given off. But positrons do exist. We'll talk more about the positron a little bit. Notice the nomenclature for the positron versus the electron, the beta particles. They're both E and beta, like the beta particles were, but that lower left-hand number is a positive one, and we'll talk about why that's important here pretty soon. You always want to write positive one. You don't want to write just one. It's not a proton, like in the proton example earlier. It's a positron. And so anyway, it's kind of a wild thing. We'll talk more about antimatter here in a little bit. There have been a lot of advances in antimatter of late, like in the last 10 years or so. And one example that just amazed me shows these two versions of hydrogen. Now, the top picture there shows a proton in hydrogen and the electron around it. That's a normal hydrogen. And it shows some quarks over there on the right. And physicists will go below the protons and electrons to figure out the quark combination, stuff like that. Well, an anti-hydrogen atom has been found, and it's being studied, which is just amazing. So instead of an electron, you have a positron, because that's an anti-electron, and instead of a proton, you have an antiproton, and you can see that the quarks over there are different. So it's amazing. I mean, you have to have really powerful magnetic fields and stuff to make them, because you don't want them to touch anything. When matter and antimatter combine, it's always bad. But just realize this is a really neat area of physics, and I sure hope there's going to be some cool developments coming down the pipeline.
You're aware that radioactive materials give off energy, especially if we expose this sample to ultraviolet light. We can see it glow. There are three different types of radioactive particle energy. There's alpha radiation, beta radiation, and gamma radiation. Here we have a nuclear scaler that measures radioactive decay. Each click that you hear is a nucleus of an atom that is decaying by giving off a radioactive particle. This is a Geiger tube, and it has a window that allows the radioactive particles to pass and records them on the nuclear scaler. What we'd like to do in this demonstration is to test our samples both for penetration and also for the distance that you must be away to receive any protection. Let's place a beta particle in our sampler. We notice that there's a slight increase in the counts. The background radiation is not nearly that fast. Here we have some small sheets of lead that we'll place there to provide some screening. We notice that even one lead sheet dramatically cuts down on the beta radiation. 2 and even 3, and we're down now to quieting the counter back to background radiation. Let's see if that also works for gamma radiation. We'll change the sample. notice immediately that more energy comes from the gamma. One sheet of lead and 2 and even 3 that quieted the beta does not quiet the gamma. We can add even a 4th. Gamma has the greatest penetration of all the radioactive particles, alpha and beta. Gamma is an electromagnetic energy wave. Well, let's see what happens as we go from being close to a radioactive source to far away. We notice that the amount of radioactivity is greatly decreased by distance.
This is a cool video for several reasons. First of all, it shows that there are 3 types of radioactive sources generally out there, alpha, beta, and gamma. And of the 3, gamma is by far the most powerful. It penetrates things a lot better than beta and alpha. Beta and alpha both have mass. They're both helium or electrons, which both have some kind of grams. If you have a alpha particle and you throw it, it will bounce off other mass, because that's what mass usually does. Mass and mass bounces off and stuff. But gamma rays will go right on through. So that's why it has the best penetrating power. It's like a wave. It's like a flashlight, all right? The flashlight won't be stopped. It just kind of keeps going. You can silence the radiation with appropriate shielding, though. They used lead there on the beta to effectively shut it down, but the gamma, as you can tell, was a lot stronger. So it takes extra shielding to protect yourself from gamma. But finally, even before they put a sample in there, that Geiger counter, which is what was used to measure the radioactivity, that Geiger counter was measuring radioactivity even when there wasn't a beta or gamma sample in the sample holder there. And that just shows that there's radiation around us all the time. So our bodies are used to some radiation around us all the time. We just don't want to have an excess of radiation around us all the time. So when you're going to have a nuclear equation, it has to be balanced. And in effect, it's a pretty chill process, but you want to have reactant protons on the left equal the reactant protons on the right. You want the atomic numbers on the reactant side to equal the atomic numbers on the product side. And you have to do the same thing for neutrons. And remember, neutrons are kind of expressed through the mass number. So you want the mass numbers on the reactant side to equal the mass numbers on the product side. As an example of that, let's look at this radium-226 isotope that's decaying to an alpha particle, which is 4,2 helium, alpha particle, and a radon-222. And if you look at the upper left-hand numbers first, those are the mass numbers. 226 for the radium equals 4 plus 222 for the alpha and the radon. So that reaction is balanced for neutrons, and then the lower left-hand numbers also balance. So 88 is the number of protons for radium. That equals 2 for the alpha particle plus 86 for the radon. So notice that the numbers in the upper left have to equal the numbers on the upper left on the other side, and the same thing for the lower left. Those numbers also have to match on both sides. So it's not too hard to do. This is the kind of problem you might see, though, and it does help to know what those different particles are. So uranium-235 decomposes through beta decay to a new product. You can find the identity of the product. And in the upper right-hand corner there, I have the symbols of the different particles that we're looking at in this section. So beta particle is the second row under alpha particle there. And you can see that the beta particle is 0 minus 1 E or 0 minus 1 beta. So in a problem like this, what I would do is first of all figure out what uranium-235 looks like. The 235 is the mass number, goes in the upper left corner. And uranium on the periodic table is number 92, so that means the lower left number is 92. So you will need a periodic table next to you unless you have the periodic table memorized, which is awesome too. But anyway, that uranium-235 then is essentially breaking down. And it's breaking down into a beta particle 0 minus 1e or 0 minus 1 beta. Either one is fine. And then something else. And for that something else, I'm just going to have a random AZX kind of symbolism there, where A is the mass number, Z is the atomic number, and X will be the symbol. So this is the equation that we have. We don't know what the missing particle is, but you can probably imagine it won't be too terribly hard to figure out. As an example, 92, the atomic number on uranium, that's going to equal minus 1 plus Z. The atomic numbers on the product side, we'll solve for Z, then define that the number is 93, stuff like that. What we want to do, 235 on the top equals 0 plus A equals 235. All right, so that's not too crazy. 92 equals minus 1 plus Z. Solve for Z by adding 1 to both sides. Z is 93. Now to figure out X, you have to look at the periodic table, which element has 93 protons, and that's neptunium. So for this problem, the balanced reaction would look like that. You'd have uranium-235 breaking down to a beta particle, and you also have neptunium-235 as the other product. Cool. So that's kind of how this works. It's not too hard. What's really kind of interesting here, though, is that in reality, one of the neutrons in uranium is breaking down, and it's breaking down into a beta particle, 0 minus 1e, plus a proton. And if you look at the symbols for electron and proton and add them up, well, minus 1 plus 1 is 0, which is what the neutron has in the lower left. 0 plus 1 on the top equals 1 on the top, which is what neutron has. So that's the reason why electrons and beta particles have a negative 1, because electrons plus protons will equal a neutron, essentially. One of the neutrons in uranium-235 is breaking down, and it's breaking down into a beta particle and neptunium-235. Here's a reaction. It's a uranium-235, but it has a different decay. It's breaking down to a thorium-231 and some other mysterious product, and it wants to know what the unknown particle is. So in this problem, we'll do the same thing. All the numbers in the lower parts have to equal each other on both sides of the arrow. Same thing for the upper numbers. So for example, 235 equals 231 plus A. So A is going to be 4. And 92 on the bottom equals 90 plus Z. Z is going to equal 2. So we have 4 for A, 2 for Z. If you look at periodic table for number 2, 2 is helium. And a helium-4 is an alpha particle. So the complete reaction would look like this. Helium-4 is a product. It does help to know what helium is versus beta, stuff like that. So keep that in mind. If you hear about a reaction that undergoes emission or decay, whatever is being emitted or whatever the decay is, it implies a product particle. And as an example of that, here's a reaction with a positron emission. So again, look for emission and decays. This is a positron emission, so that means a positron, that 0 plus 1 beta, is going to be a product. So emission and decay, whatever is being emitted or decaying, it's going to be a product. This is a polonium-207 breaking down to a bismuth-207, and in the process, a positron comes off. Sometimes you see a capture. This is mostly used for neutron capture, but sometimes for electron capture as well. Whatever's being captured will be a reactant. So here's an example of a neutron capture reaction. Fluorine-19 can absorb a neutron essentially to make fluorine-20. So a neutron capture means that whatever is being captured is a reactant. The neutron here is a reactant, and you can figure out the other pieces from there. There's lots of types of particles and lots of types of decays. This just shows some random ones: alpha decay, beta decay, positron emission, electron capture, gamma emission, spontaneous fission. Focus on the first parts. Decays and emissions, again, are going to have a product, while capture will be a reactant. Gamma emission just means a gamma is being emitted, all right? And spontaneous fission is a little bit more complicated for what we need, but it basically is one piece breaking down to lots of smaller pieces. But the ones we can predict anyway, is just, cool scientists, will be the decay and the emission ones. Don't worry about the spontaneous fission. That would be pretty crazy. An unstable element usually decays through several steps until it gets to a radioactive or an isotope which is stable. And this shows the decay scheme for uranium-238, and it actually goes through 14 different steps before you finally get to stable lead-206. So all of those other isotopes listed on there are unstable until you get down to lead-206. So you'll see here that there's green arrows and there's red arrows. And the green arrows are basically having an alpha particle emitted, because you can see like in the top there that uranium-238 is going to a thorium-234. That means it's emitting an alpha particle. On the other hand, all of those red arrows, those are beta decay. So when a particle that's being emitted is an electron, and so in thorium-234 there, it's going to turn into 234 protactinium. That's Pa, not Pennsylvania. Sorry, Pennsylvania. But anyway, that's an example of a beta decay, and that further decomposes into the very unstable uranium-234 before you start getting into alpha decay once again. So again, it's really crazy. People have studied this. They create elaborate pieces, but you could write the balanced reaction for all of these. All right, no problem. Alpha decay means it's kicking out an alpha particle. Beta decay means it's kicking out a beta particle. Now, this positron thing is really wild, all right? And Paul Dirac was actually the first person to predict antimatter back in the 1920s, and he thought it might be identical to regular matter except for its opposite charge. And positrons are the first example of antimatter that, as I know, were ever experienced. Positrons are anti-electrons. Now, when you have regular matter and its antimatter component next to each other, when they combine, it leads to what's called annihilation, which is basically when gamma rays are emitted. And notice in that balanced reaction, the beta particle, the left-hand side, and the positron, the 0 plus 1 e particle, when those two particles come together, they create two gamma rays. And that's very, very common. Two particles in create two gamma particles. Two gamma rays would be a better way to say it. There's something in symmetry and quantum chemistry we're not going to talk about, but that's why that happens. Pretty cool. But more interesting than not, up at OHSU, they actually use this. If you've ever had a PET scan, or you knew someone that did, PET, by the way, stands for positron emission tomography, they're essentially using antiparticles to create an energy spike that is detectable. Then they can search for your soft tissues and stuff. Anyway, it's really cool stuff, and there's practical uses. It's not just cool Star Trek things like I'm talking about, basically. Lots of examples of annihilation reactions. Here's the neutrino and an antineutrino. They combine as well to make two gammas. If you had a proton and an antiproton, they would combine to make two gamma radiation. Amazing. All right. Neutrino is another one of these subatomic particles that we're not going to talk about. Very cool kind of stuff. Anyway, go with the flow. Another type of system you might see in this kind of section would be a metastable nuclei. And if you have an electron in an atom and you excite it, it relaxes back down. And we saw back in Chem 221 that this is the basis of emission spectroscopy, and it's what's used for absorbance spectroscopy. And the wavelengths that come out are usually ultraviolet, infrared, visible, stuff like that. Well, the nucleus itself can be excited as well. So if the nucleus gets excited, it creates this metastable nuclei. And just like electrons, the nucleus can relax back to a ground state. But because everything in the nucleus is so high energy, a gamma ray is usually emitted. This is an example of a metastable nuclei reaction. And notice the little M there on the left-hand side. Tc is technetium. So they call the M-tet version of technetium, they call that metastable technetium. And what happens is when it relaxes back to regular technetium. So you can see the M is gone. And you also have a gamma ray. So the M just means it's metastable. It's an excited nucleus. You can think, if you will, that instead of having a nice distribution of protons and neutrons kind of mixed together, maybe you have a lot of protons on one side and a lot of neutrons on the other. So it's a very unstable kind of configuration. And it will decompose back to the regular version. In the process, a gamma ray is emitted. So again, there's no change to atomic numbers, no change to the mass numbers. You just have a gamma ray emitted. Medical imaging, also used at OHSU. This is a real common procedure, and you can have technetium, metastable technetium, made pretty readily. It decomposes to regular technetium, which further decomposes, if I remember, to molybdenum. So it's just something to think about. The medical applications of a lot of this stuff are quite fascinating. So it's more than just like cool science fiction stuff, and it is pretty cool science fiction stuff, in my opinion. However, there are some real practical uses as well.